Okay, let's go. So this is a special live. I'm recording the async lecture. So this is lecture 10. I know it says 11 here, but the midterm, there's no lecture on midterm day. So this is the async lecture. I'm streaming it live just because of logistics. It's easier to do this. So if you happen to catch this live, feel free to interact in chat and chat with me and stuff. But really, I'm just doing this for the recording. I won't be available on June 30th, so I have to record this ahead of time. So if you're watching this just on YouTube and you're wondering why Lecture 10 is being recorded before being streamed before Lecture 9 graphs, the 9th lecture, that's why. It's just because I have to record this async, and I'm doing it before graphs. It's actually June 23rd right now, so at the time of recording. So everything's a little bit out of order. I'll put a link on the website to this video. Well, if you're hearing me say that, you already found it, but I'll put a link right here once it's recorded. If you're watching this, the link's already there. So let's get started. This is all live coding, and this is all about runtime. And specifically what I want to do is, what I will do in this lecture, is get a good feel for what the different runtimes mean. We talk a lot about constant runtime, linear runtime, O of n squared, O of n log n with our trees. We talk about that a lot, and we saw a little bit with trees last lecture. We turned our tree into a linked list and saw the difference between log n runtime and linear. We want to dive into that quite a bit further and also explain a bit about what we did with the tree runtime. We had some strange syntax with this time it. I'll actually start with talking about the syntax here because it's a really cool piece of syntax in Java. Really simplifies our lives quite a bit. It's pretty advanced. It's not something you need to know in 116, strictly speaking, but moving forward in your career, it's something you're going to want to know to be able to write cleaner code, better looking code, and code bases that are a lot less cluttered. So let's jump into that. I have just a little bit of code given, and then most of today is just going to be a lot of live coding. We're going to start with talking about some data structures, and we're going to move into this sorting. We already did the trees last time. We'll move into sorting and talk about the different runtimes of sorting. We'll look at the runtime of the sorting method we already saw, insertion sort. And then we're going to build merge sort. We're going to write merge sort and then compare the differences between insertion sort, which is O of n squared, and merge sort, which is O of n log n, and see what the real difference is between those runtimes. We'll run it on a whole bunch of different sizes for n and see what the actual difference between those runtimes are. So with the code that we have started, we have this timeable interface, which has one method, run, which takes no parameters and returns void. So everything that we want to time is going to have to implement this timeable interface. Timing utils has a static method that will take a timeable, call its run method, and measure how long it takes to run. We can get the current system time in milliseconds. This is going to be I wonder if it says it right here. Yeah, it does. It explains all about Unix timestamps right here. So this is the number of milliseconds that have occurred since January 1st, 1970 on midnight at the time zone plus 0 at UTC. So at one very specific moment in time, it's how many milliseconds have passed since then. This is what we really like to use for storing dates because it will be an exact moment in time. This is a very exact moment in history, and we're counting the number of milliseconds since then. So it's a very exact measure of time. As opposed to using local time where you have to worry about things like daylight savings and leap years and time zones. This ignores all of that, cuts through all the bullshit, and just gives you an exact moment in time. And then we take these timestamps. No end users want to see these timestamps. It's just a big number. But we take these timestamps. This is usually what we like to store in our databases. And then when we need to show the end user the time, we'll take that timestamp and then convert it into their local time according to their time zone. What if it's a leap year, or taking leap seconds into account if need be. All the complexities of taking finding a local time. We'll do that at the time that they request the date. But we store dates according to one person's local time and then try to convert it to another local time. Just a lot more complexity. So we really like these. We're not really using the full effect of that because we're just going to subtract them. So it really doesn't matter what this is in absolute terms. we're just taking a difference today, so we're throwing away a lot of the usefulness of it. But we are taking the difference of 2 exact moments in time, and then figuring out how many milliseconds it took to run our code that we're trying to time. So what this implies is that if we want to use this method to time something, we need a class that implements the timeable interface. And then we're going to create an object of that class, and then call the timeIt method with that object. So what we'll have to do, what has to get done, let me rephrase that, is the thing I want to time is going to be a class that implements the timeable interface. And then I'm going to have to override the run method. So I'm going to have to override a method. It has to be public. It returns void. It's going to be named run, takes no parameters, and has the code I want to test for runtime. And maybe I have a for loop for int I equals 0, I less than a million, I plus plus, let's actually have this do something just for our first test. A long number, because I'm not creative, equals 0, and let's take the sum of all the values from 0 to a million to make sure we get a million. I'll change this to less than or equal to. Well, I guess we can go 1 to a million instead of 0 to a million. And then do number plus equals I. And we'll print I number to the screen. My mind switched to Python right there. S out number. So say I want to test this code. This should be a linear runtime algorithm. We're iterating from, actually let's make that one a little more clear. Int n equals 1 million. I almost said, if you're wondering why that's a long, that'd be a good question to ask. I'll explain it, but I'm like, well, probably nobody's watching live right now. So you can't really ask at an async lecture, but force a habit if I say that a few times. Just force a habit. Okay, so I'm making this a long because I think summing up from 1 to a million, I think it's going to overflow an int. Actually, no, I don't think it will. We could probably get away with an int here. I'm going to keep it a long just so I can talk about this. But if we're afraid we're going to overload an int, the max value you can have for an int, can I write a main method in a, I've never tried to do this, but write a main method in an, no, I'm not in an interface. But now I have to know, can you write a main method in an interface? I'm going to say yes, that's my guess, but let's find out. Yeah, you sure can. I'll do it right here. So if we print out integer.maxValue, this will print out the largest value. It's like 4.3 billion, I want to say. I always forget the exact numbers. 2.1 billion. 4.3-ish is if it's an unsigned, you get double the max value. We have to use 1 bit for the signed bit, so we get half as much magnitude. I always get my numbers mixed up, but it's in the billions range. So if we're going over 2.15-ish billion, then we can't use an int anymore. We have to use something more, either a double or a long. We have to use something else. So if you're ever worried you're going to go over, you know, if you're going to even get close to the billion range, you should really use a long, or think about something else. There's also something called big integer that lets you have arbitrarily large integer values. So if you need something bigger than a long, go for big integer. Not going down that rabbit hole right now, but that's why I have long here, because I thought for a moment I might overflow. Actually, I don't know. I don't know. We'll find out when we run the test. We're about to run the code, so whatever. We'll figure it out. And then what I need to do, Here's my main method. I'm going to have, eventually we'll use this value of n to figure out how long it takes to handle some value n, because we measure all our runtimes in terms of n. It's either O of 1, meaning n doesn't matter, it's constant time. O of log of n, meaning the runtime grows logarithmically with the increase of n. O of n, which means that it has a linear runtime. It's a linear relationship of n to the actual runtime, or log n, n squared, and so on. But it's measured in terms of n. N, for our purposes, I hard-coded to 1 million. We could go and change it in the other class, but I'm building up to something a little cleaner than what we're doing right here eventually. So what I now have to do is create a thing I want to time, which we can actually, since this implements timeable, can just do timeable right here. Timing method, that's not the best name, but and then new thing I want to time. And then I can finally use my timing utils method. So timing utils.timeIt, which takes a timeable and give it timing method. By polymorphism, thing I want to time implements timeable, so I can store it in variables of type timeable. I can store it directly in the variable here, or I can store it in a variable type thing I want to time. It is still a timeable, so it's a valid argument for timeIt, which takes a timeable as a parameter. So timeIt takes this object that implements the timeable interface, which will call its run method, which in our case is going to sum up the values from 1 to 1 million and time how long that takes, and print out, I'm saying to insert values, that's what we're eventually going to do. Let's just make that cleaner. We'll shelve this for now, and I'll just print out how many milliseconds it took. So now we're finally able to run this and time some code. So it's summing up the values from 0 to 1 million or 1 to 1 million, and we did overflow. I can't do quick maths in my head, right? It's about 500,000 squared, I guess. But yeah, we would have overflowed an int. And it took 3 milliseconds. 1 million is a tiny number to a computer. It takes like no time to do that. If we do an int, by the way, it's a little off track for timing, but let's do this. If we sum up the values using an int, we actually get a completely different number here. That's because we overflowed an int. We went further than what an int can store. So what we do is keep wrapping around. If we have integer.maxValue, this is the largest value you can store in an int. So what's that value plus 1? If we print that to the screen, we'll actually get the largest negative value we can store in an int. So it actually wraps around to the absolute lowest value you can store, negative 2.14 billion. And then starts climbing up again. So as we're summing up all the values to 1 million, we're constantly wrapping around and going 2.14 billion, going back to negative, going all the way back up to 2.14, and constantly wrapping around. It's not what we want. That's why we made this a long, so we actually get the right result. When we run it here, we're going to get a significantly different number here. And that is an extremely difficult bug to find. If you're overflowing your ints, or underflowing, if you go too negative, it'll wrap around to positive. If you're underflowing or overflowing your ints, that's a tough one to find. It's one of those things where you just got to be always in the back of your mind thinking, might I overflow this? If there's any chance you're going to overflow it, grab yourself a bigger container for that number. Because if we use long.maxValue, long.maxValue is pretty friggin' big. We have 63 bits of precision, so 2 to the 63 minus 1 is going to be this value right here. We can store much, much larger numbers in this thing, in these longs. Okay, so this is a bit of a pain in the ass to do though. So I want to get to that other syntax we saw with trees. So let's rewrite this code a little bit. Instead of creating a brand new file with a brand new class that implements timeable and overrides the method that we're implementing, then create an object of that type. All of that still needs to happen, but that's tedious as hell to actually do it all. This is where Java gives us a better way of doing things, a better way of expressing the same thing. And I want to stress this, it's doing the same thing. Everything we just did still has to happen. All of that stuff has to happen, but Java does give us different syntax to kind of hide all the details. And that syntax is doing new timeable. This is something that I tell you all the time, not all the time, but when we're talking about interfaces, I say you cannot create a new object of type interface. You can't instantiate an interface. That's insane. Like, you can't do that. That's just not allowed. You can't do that. Which is true. You cannot implement an or you can't create an object of an interface. You can't instantiate an interface. You can't instantiate an abstract class. But Java does let you pretend you can. I can say new timeable, and then in braces, what I can do is put my override annotation and override. I think I have my syntax off a little bit, but we'll get it out here anyway. And we can actually override this run method right in line. Public void run. Get my syntax off. What am I? Oh, I just need my braces, or my parentheses there. And we can implement this method in line right here. So we can say new timeable, and this will create a timeable object. Well, kind of. But we can define a class that implements the method, that implements the interface and overrides the method in line instead of having to create a separate file to do that. We can just create it in line. We just say new timeable, and Java says, okay, you want a class that's going to implement the timeable interface and override all of the abstract methods in the timeable interface. Let's just do that right here in one place instead of messing around with a new class and creating a new object and all that. This is called creating an anonymous class, because we are creating a new class that implements the timeable interface. We're just not explicitly creating it, and notably we never name it. I have trouble even coming up with stupid names when I created that class, because I'm never going to actually do that when I code. It's just something I'm going to use an anonymous class for, something I don't name because it's an anonymous class using this syntax. So this is much cleaner syntax to be able to do this. And it does the same thing, except now I can pull out my n and put my n equals 1 million out here. We can still see n. It's still in scope at this point. And now I can control n the way I want to for the rest of the lecture. And we get the same effect, same results. We can bump this up to 10 million. Remember, this is a linear runtime algorithm, so how long does linear take? At 2 million or 10 million, it's still pretty damn fast. 100 million, we might overflow. Are we going to overflow a long? I don't think so. And 54 milliseconds. Can we get to 1 billion? We sure can. But it's taken about half a second now. At 1 billion, it's taken a little bit longer. 1 billion is still a tiny number to a computer, but we are doing quite a bit of additions with pretty large numbers. You know, it takes a little bit. It takes a little bit of time. But 1 billion, we do purchase computers based on how many billions of computations it can perform per second. So this is still under a second, half a second, less than half a second to perform this. Because my processor is running at, I don't even know, 3-4 billion cycles per second. So it's not surprising that this is under a second still. Like, I can do multiple billions, and I'm doing an addition, which is in the instruction set of the CPU. It's going to take 1 clock cycle to perform an addition. So billion's really not a big number if you have linear runtime. Once we have worse than linear, it's going to start being a problem. But with linear, it's not a problem. But with this syntax, we can actually simplify this quite a bit. You can see the warning. I kind of hovered over it for a while. It says this can be replaced with a lambda. So let's talk about lambdas too. This is the same thing. It's doing the same thing, but it cleans up this syntax a little bit more. So if you don't like how verbose that was, which it wasn't that bad compared to what we started with. Oh no, I'm going to blank on the syntax. There it is. And then I got a bunch of extra crap here. I need my closing paren. Okay. This is a lambda function. Don't let the name deceive you. This is a little bit of a pet peeve of mine. It is not a function. Despite the name, it's called the lambda function. This is what we call syntactical sugar. This is still doing the same thing that we were doing before. It's creating an anonymous class that implements the timeable interface and overrides the run method. All of that stuff is still happening. We just get different syntax. Syntactical sugar because it's sugar that syntax that just looks cleaner, looks nicer, but doesn't actually do anything more. We're not doing anything different. What we're doing here is pretending that our object-oriented language has some functional programming features, i.e. lambda functions. Java doesn't have lambda functions, but it has lambda functions syntax, and they just call it lambda functions to make sure it's nice and confusing. But this has nothing to do with functional programming. It's still object-oriented programming. There's just an anonymous class being created. You can use this syntax in the specific case where you have an interface that has exactly one abstract method. Then you can use the lambda syntax, the lambda function syntax, and since I'm giving this to a timeIt method, which takes a timeable interface, it takes something that implements timeable, Java knows that if I give this a lambda function syntax, that knows to create an anonymous class, implement the interface, blah, blah. It knows what interface I'm talking about. It's not going to make me say @override, the method name, the return type. It already knows all that. So I have the parameter list here. Parameter list for this method is empty. So I don't have to put parameters here. But if your abstract method took parameters, you would put them here, A, B, or whatever, whatever your parameters are. So you can use them in your body of your method here. I don't have any parameters, so I just have an empty parameter list and then the body. I don't have to name any functions, methods, classes, whatever. It's all anonymous. And this does the same thing that we did before. I cranked it down to 1,000, so it should run in 0 milliseconds. But that's what we're doing. So that's that syntax. We did see that with the trees. I really glossed over it. I said this is just cool syntax that we get to use because, well, that just wasn't the lecture where I have time to talk about that by design and all that. But this is the lecture where I wanted to clean that up and just talk about what that weird syntax is, because it doesn't even look like Java code. It looks like something from an entirely different language. This is a fairly new feature from Java, and it is Java stealing this from other languages that have real functional programming and said, programmers like that kind of stuff, so let's give it to them. Okay. So now let's get to some more runtime stuff. We got a bit of setup here. What I want to do next is start comparing array lists and linked list. We talked about these two data structures, and linked list really is the first data structure that you see, assuming you're coming through 115, 116. In most places, I think it's the first thing you'll see. It's the first data structure you'll see that doesn't really give you more power. It gives you more efficiency for certain tasks. And we talked about those tasks a bit. We built stacks and queues and talked about O of 1. Let's get a good grasp of what that is. And for that, I'm going to create an interface here called append prepend data structure. And you'll see the code that I'm going to write today, it's all in the repo right now. I deleted it for this lecture so I can live code it. I actually call it append prepend data structure in the repo. If you create an interface by convention, a lot of devs like to name interfaces starting with a capital I, abstract classes starting with a capital A. I'm going to, just to be different than the repo, I'm going to avoid the I. With modern IDEs, it's really unnecessary because I get this big old icon right here with the I in it that tells me it's an interface. I don't need a naming convention to show me that in 2026. But in the olden days, that was a good way to, at a glance, tell what's an interface, what's an abstract class. So some older devs will still do that. So I'm going to have this interface, which is going to have two methods, append and prepend. So void void append. This is going to have to take a type parameter. Oh, if I can get over there. It's going to have to take a type parameter. Let's name it J. Type parameters, just recall it's one single uppercase letter. You can really pick whatever you want. I usually pick T for type, but I don't know. I decided to be, I don't know, I just wanted to look at a different letter. Sick of looking at T's. So append is going to take one value of type J. I'll just call it value. And void prepend is going to take a value of type J and prepend it. So we want to add either to the beginning or end of the data structure. And I want to implement this interface twice, once for an array list and once for a linked list, and time the difference between appending and prepending for our data structures. So let's create our array list append prepend. I can't call it ALAP. Array list append prepend. I'll just spell it all out. And this is going to implement the append prepend implements append prepend ds of J, and I'm going to need to take a type parameter. It's going to tell me this type parameter doesn't exist. There's symbol not found, probably cannot resolve symbol, because that doesn't exist. We put the type parameter list right after the name of the class we're creating. So this doesn't create a type parameter list. This is the interface I'm implementing. That's just not where the type parameter list goes. It goes after the class I'm creating. So now I have a type parameter list named J, and I'm going to send J to the interface and say I'm implementing append prepend ds, and also in append prepend ds make the type parameter the same as whatever the type parameter is I'm getting for this data structure. So now I need to implement my methods. I need to override. I'm going to start using shortcuts for this one. The general rule of thumb, I don't think I found a good spot to say this in a lecture, but for the class, I just avoided using autocompletes or anything so far. This is the first time I'm going to use it fairly heavily. So the rule of thumb in 116, and just a good idea overall, just throughout your career, whenever you're programming anything, side projects even, is autocomplete can be fine. Any tools really can be fine if what they write for you is what you would have written anyway, and you're using them to save time. Once you have autocomplete that's writing something that you wouldn't have written, and even more detrimental, something that you don't understand. If autocomplete wrote something you don't even know how it works, you're using it wrong. You're doing it wrong, in my opinion, I guess, but I feel like that's not very controversial. If you're using code that you just don't understand at all, you will run into a wall at some point and probably get into trouble at some point. A lot of developers who are doing that kind of stuff, they run into security issues. They leak data, they leak their API keys, and somebody racks up a big bill for them. And then they complain on Twitter. It's funny. But anyway, so I'm going to do this implement methods. I'm going to override append and prepend, and it's just going to give me the boilerplate code for those overrides, so I don't have to just type those characters out. I know exactly what I'm going to type there. I just typed these exact methods here without the override annotation. It's just saving me some typing that I would have done anyway. I fully understand what's going on here. I'm just doing that to save time. That's always fine. And of course, I'm talking in the context of 116, I'm talking about the AI policy, the academic integrity. If you're using autocomplete and you understand exactly everything that it's doing, and you would have typed that anyway, I got no beef with you. But once you don't know what it's doing and you're not learning, you're cheapening your educational value, and then not learning what you need to learn, and then going out to the world and not being able to get a job, that's where I've failed you. Like, I need you to get a job. Like, that's why I'm here, is to help you get a job. So I can't let that fly. Okay, so we have our syntax. We got that spiel out of the way. And what I need here is the actual data structure that I'm going to create. So private array list of j, I almost did t, of j, I don't know, my list equals new array list. So I have my array list here. I don't really have a way to get these values. I do have to cheat a little bit here. What did I do to get these values? I hid the final code in here. Append, prepend, array list. Oh, I just didn't have a way. So we're not going to be able to. I don't like that. Let's add another method here to print the whole thing out. Because I want to be able to verify that the value, that there's actually something happening. We don't have any way to verify that without that. So let's override our brand new public void print method. And when we append this dot mylist dot add is our append method for an array list. It adds that value to the next available index. That's effectively append. So it's our add method. And then this dot mylist dot add with an index value. Here we're inserting at the first index, so we're prepending this to the beginning of the list. And I get this warning. There's a special method for this, add first. I don't know. I don't like using the special methods for that. I can read that this is going to add in index 0. I don't have to think about what add first does, if it does any extra stuff. I don't know. I'm going to leave it like that. I like it that way. And then for our print, we can just print out the list. I'm just going to use the array list print method, and I don't have to do anything fancy there. I could iterate over it and print one at a time. I'm just going to print the whole thing in one go. Okay, so this is array list, append, and prepend. To see this in action, we can get rid of our test here. I'm going to create my append, prepend data structure of double data structure. Most generic name possible. New array list append prepend. And then I want to add to this thing. So I want to for I equals n. Again, I'm using the autocomplete there. It's exactly what I was about to type. I would have typed that exact thing. Maybe my spacing would have been different. I think I usually don't do spaces here. Maybe here either. I'll give a little bit of my style in there. Oh, and I definitely don't do the space after the 4. I think I usually do because I use auto. Yeah, the auto is going to add those for me. And I want to do data structure dot append tree timing. I forget what it's called. Time trees dot random double. I want to use this random double that we wrote. I just don't feel like writing it again. This is the method that's going to give me a random double between -100 and 100, rounded to 5 decimal places. That's the one that we used last time. Just give me a random double that doesn't have a whole bunch of trailing decimal places. I just think it looks messy with that. So I'm going to add n random doubles, which is 1,000 right now. And for good measure, let's print that to the screen. Data structure dot print. just to make sure we're actually doing something. And now we are actually inserting things. So I'm going to switch to my other print statement. How long does it take to insert n values here with append for our array list? So that's how long does it take to append 1,000 values. And remember, this is going to add in, this is going to, what am I saying? This is going to have that resize factor. So with our array list, appending to the end or adding any values to an array list, and increasing its size, every once in a while we will have to throw away our old array, create a brand new array, and allocate all that memory, copy everything over. A very expensive O of n operation every once in a while. So an insert at worst case is O of n, and we're inserting 1,000 values. So n is 1,000, and each insert could be O of n. That seems like we might have an O of n squared algorithm, because we have n insertions, each one, which worst case is O of n. So we have O of n times O of n, that's going to be O of n squared. But with 1,000, we only get 12 milliseconds. Let's crank this baby up. Let's go right to 1,000,000. There's not much interesting for this one, so I'm not going to, blanking on my expression, but I'm not going to belabor the point. Even at 1,000,000, it's going to take about half a second to be able to insert 1,000,000 values. So in effect, that doubling, that every time we run out of space, we create a new array of double the size and copy all the values, that actually turns out to not hurt us that much. It actually doesn't really matter at all. I mean, it could matter in very specific situations because you don't know when that's going to happen. A handful of these insertions were significantly slower than the rest of them because of that doubling, but it ends up spreading out over all of the insertions, specifically because we double the size. It spreads out that cost, and if we're inserting n values, it actually ends up being linear runtime. This is something we call amortized O of n runtime. It's effectively O of n for us, even if it's not literally O of n in terms of asymptotic notation, but we call it amortized O of n because it is O of n. CSE116 will go through all the math and explain exactly why that is the case. For 116, I get to just leave it at, in that cool, it's amortized O of n, half a second to insert 1,000,000 values. And at this point, this should be the first time where we really get to feel this. So I'm inserting 1,000,000 values and then printing to the screen. And this takes 427 milliseconds. Let's run it a few times and kind of take a pseudo average. 381, 430, 391, 424. So like 410, 400, if we're being generous, about 400 milliseconds, about 0.4 seconds. I'm not going to change any of the code. I'm just going to get rid of this print statement, which is printing 1,000,000 things to the screen. We can verify we have all these doubles rounded to 5 decimal places. Let's run this again. And it took 137, 131, 136, 135. This is an important thing to know when you're programming. Printing to the screen is actually a very expensive operation, a very slow operation. So most of the runtime we were getting there was just my print statement. This can lead to some really interesting bugs that can absolutely drive you insane. Is if you have your code with all your debug statements in it, and you finally debug everything, you get it working, it's like, oh, great, this is working. I'm going to remove all my debug statements and then ship it. So you comment out all your debug statements or delete them entirely, where you print got here, made it here, the value of x is this at this point. You remove all your debug statements, you run it again, and all of a sudden it doesn't work anymore. Because the way the timing worked with your print statements, it actually slowed down enough to be able to get things to work. Usually when you have what's called a race condition, when you have two separate things happening in your program simultaneously, and whatever one finishes first is going to affect the behavior of your program. And if one of them finishes first, it's a bug. The other finishes first, and it's fine. That's a race condition. and you might have been slowing down one of those threads just enough with your print statements to be able to have the race condition work in your favor, and then removing the print statements, all of a sudden you're losing the race condition and you have a bug and your program crashes. Absolutely drives developers nuts. So just always keep in the back of your mind, there's a lot of things you got to keep in the back of your mind when you're programming, but print statements are actually pretty expensive. In this case, it significantly affected our runtime. So always be careful with your print statements. I'm printing 1 million doubles to the screen. Like we saw, it was a lot of text being printed to the console. That's going to take significantly longer than appending 1 million values. And we can even go to 10 million. This is linear, so we'd expect this to take about 1.5 seconds. And, well, less than 1.5 seconds. So somewhere we got some overhead. Maybe we didn't, maybe we're far... maybe we're right next to the next doubling, a lot of factors can happen. But 10 million values, by the way, if you have a data structure, one of our takeaways here, if you have a data structure that needs to store 10 million values and you need to run a linear runtime algorithm, that's what we have right here, is a linear runtime algorithm, linear in terms of n. So we have some constant times 10 million to be able to add all these values into our data structure. It's taking less than a second. So about a second. If you have 10 million values and you need to perform a linear runtime operation on it, your question is, can I afford something on the order of seconds? Like, can I afford a second? Maybe it takes 2 seconds if you have a higher constant. Can I afford that much runtime? And depending on what you're doing, the answer might be yes, the answer might be no. There's a lot of different measures based on what you're doing. If this is a web page that's loading, and you're making your users wait an extra second for that web page to load, that's going to be unacceptable in most cases, unless I don't want to go down that rabbit hole, but unless you're writing an app where people are stuck. Like, you can't get away from UB learns. If UB learns takes 10 seconds to load, well, we're all just fucked and we have to eat it. But any app where people have a choice, like YouTube taking an extra second to load, well, actually a lot of us would probably watch YouTube still anyway, but an app where you're like, I'll check this out. It's an extra second is pretty detrimental. A lot of users will just leave. I'll leave a website. What's up, Kajiji-san? Sorry if I butchered that. So that's going to be unacceptable. But if you're crunching data, if you're doing research and you're generating graphs for your paper, and you have to wait a second, like that's basically zero time. It is completely negligible. So it really depends on your application whether a linear runtime algorithm is useful to you or not. Okay, so linear is pretty cheap. That's the big takeaway there. Of course, unless you're in the billions range, then you can't use your linear runtimes anymore. If we go to 100,000 and it's going to take like 10 seconds, it's starting to be a little more unacceptable in a lot of different cases. Oh, and I don't remember if I mentioned this last time. I think I did. But the underscores, you can put underscores wherever you want in your ints. Like this is still a valid int. Underscores will be ignored. They can't be trailing. They can't be leading. But in the middle of your integer values, you can put as many underscores as you want. So it's a nice thousands separator to make our numbers more readable when you have these large numbers. And it took about 7 seconds for 100 million values inserted into an array list. Not that big of a deal. Let's crank this back down to 1,000 and prepend. Now remember, prepend is a linear runtime operation, and it's legit linear. When we insert at index 0. Let me get the runtime first. When we insert at index 0, everything in the array list has to be moved down by 1 index to make room for that new value. So at 1,000, we got basically 0 time. Let's go right up to 100,000. So if we're inserting n values, and each insert is a legit n runtime, not our amortized O of n, doubling only happens every once in a while. No, this is legit O of n. So this is an actual O of n squared method that we have here to prepend n values into an array list. And now already we're almost at, we're at 0.6 seconds at 100,000, at 1 million. At 1 million, our n squared runtime algorithms are becoming very quickly unusable in most situations. Again, unless you're like generating a graph, you can let it run overnight or whatever, then who cares? But at 1,000,000, most applications, you're going to have extremely slow web page loads, you're going to have extremely laggy video games, you have very unusable apps for your users. It's just not going to be acceptable in most applications. If you're doing, again, if you have your own process that you're using for your own purposes to crunch some data or whatever, yeah, maybe you can wait a few hours. But at 1,000,000, this is still running. I'm prepending 1,000,000. Remember at append, this was less than a second still. We got all the way up to 1,000,000,000 before it started taking a couple seconds. With prepend, even at 1,000,000, this is where your choice of methods and your understanding of your data structures is going to come in absolutely critically. Once you get into these higher values, these larger data sets, it's absolutely critical that you pick the right one. Notice at 10, was it 10,000? There, finally finished. 70 seconds, it took over a minute to prepend 1,000,000 values. Remember, append at 1,000,000, 1/10 of a second. It's a big difference. That's the difference between linear and n squared, is significant once you get into these higher values. But prepend, even at 10,000, 10 milliseconds. So if you have less than 10,000 elements, you know what? Don't stress about your data structures that much. Even your n squared runtime algorithms are fine. But once you get into those larger numbers, once we're dealing, we deal with this kind of stuff with grades in Autolab. When we have across all of Autolab, I forget off the top of my head the numbers, but we're up to hundreds of thousands, maybe millions of total submissions in Autolab that are stored in the database. So if we got to go through all those submissions and we're running an n squared algorithm, we're cooked. Like we just can't be doing that. But if you have 10,000 values, if that's what your app is working with, you got 10,000 users or 10,000 total orders or something. Use your n squared algorithms. Who cares? Be sloppy, be messy. Forget everything you'll eventually learn in 250 and everything you're learning here. Whatever. Use an array list for everything. But once you get higher than that, you got to start thinking about these things. And when you get hired on the job, usually any company is going to have large data sets. You're going to have to be thinking about this kind of stuff. In most situations, obviously, some of you won't, and then, don't come back to me and say, Jesse, you lied to me. Yeah, there are some places that just don't work with a lot of data. That's fine. But for the rest of us, linked list DS, what did I call it? Linked list prepend, append. Append, prepend. I did that backwards for my array list, but you know what? Whatever, I'm keeping it. So let's do the same thing with our array list. Just to make a point, let's make this O. Is that the most obnoxious type parameter letter to use? It might be. Implements my append, prepend data structure of O. I used a different letter just to emphasize that this is a different parameter list than the one inside append, prepend. So this is effectively saying whatever O is, whatever type that is, assign that type to J in append, prepend. So I can have different data structures there. I'm going to do my autocomplete here just because I don't feel like filling in the method boilerplate stuff. And I need my linked list. So I'm going to use the linked list node of O. Head equals new, oh my goodness, equals null because the linked list is initially empty. This is going to be private. And I need to import linked list node from topic for linked list node. That looks fine to me. Append, let's start with prepend because it's easier. Prepend is head, this.head equals new linked list node of value head, and that's prepend. We're creating a new linked list node with the value we're prepending. the next is going to be whatever the head was, and that new node I just created is now the new head. Prepend is a very easy operation. In fact, it's an O of 1 operation for a linked list. Very easy, clean, efficient data structure. We do have to allocate some memory on the heap, so it is a little more expensive than appending into an array when we don't have to resize the array. But it is a very, very cheap operation. In terms of asymptotics, it's still O of 1, but the constant, I'm not sure if I mentioned that this semester yet, but what big O notation does, it says on the order of magnitude of, say, linear or constant or something. With big O notation, we ignore all of the constants. So if I have an O of n runtime algorithm, it might be 5, the actual runtime might be 5 times n plus 15. That might be the actual runtime in terms of number of steps to be able to run the algorithm. Or it might be 1,000,000 times n. We don't know what that constant is. It might be 1,000,000 times n plus 1,000,000,000. That might be the actual runtime. But all we're saying is that it grows linearly with the input size. It might grow 1,000,000 times the input size, but it will grow linearly. So with asymptotics, what we're really concerned with is what happens when the input sizes get very large. What happens out to as we approach infinity, which sometimes isn't the most useful thing. If your constant is actually 1,000,000, that might be unusable for your applications. So asymptotics aren't perfect, but they do give us the order of growth in runtime. So eventually, an O of n squared, no matter what the constants are, runtime algorithm is going to be slower than a linear runtime algorithm for some value of n. There will be some sufficiently large value of n where the slower growing method will be faster. Okay, with that out of the way, there's 250. CSE116 will give you a much better primer on big asymptotic notation, big O notation. I'm giving you the very, very surface level intro, just enough so we can do these comparisons that we're doing today. That's all I really need from you in 116. So let's append, and I'm going to write this with a loop. I've done all of my linked list methods using recursion so far. I am going to use this one in a loop, partly because we will start overflowing the stack if we do this recursively. So I'm going to say, what am I going to say? Linked list node of O node equals this dot head. If this dot head is null, so if my list is empty, then this dot head equals new linked list node of value null. Else, I'm going to, in a loop, initialize a node to head. I'll get a little fancy with this. If I'm going to show you a loop, loops is usually what most students do on their homework, so you probably already used loops and wrote methods using loops. So I'll get a little fancy with it here. I'm going to say node, node dot get next. I gotta think a little bit. Oops. Well, get next is not null. Node equals node dot get next. Oh, I'm gonna get fancier than I want it to be here. All right, this might look a little gross. I might have to rewrite this just to make sure it's legible. But I'll still do this for those of you who want to see some, I don't even want to say neat, different, weird syntax, just weird ways of writing code. Just using the things that we know about code, we can do some kind of wacky stuff. So I'm going to write this loop to be able to find the end of the list, and then do node.setNext equal to new linked list node value null. Oops. So what I'm doing here is setting a node equal to the head of the list, and then I'm using a for loop in a really strange way to be able to navigate to the end of the list. So I'm saying, well, the next node isn't null. That means I know I'm not at the end of the list yet. Then advance to the next node. Set node equal to the next node. And then check, is the next node null? If not, get to the next node. So at the end of this loop, node is going to be the last node in the linked list. And this is a loop with no body. You can actually just cap off a loop with a semicolon. You don't need a body to the loop, which usually you have bodies to loops, but every once in a while there's a situation where you don't really need one. So I'm just going to cap it off with a semicolon. And now after this loop ends, I know node is the last node of the list. So I have my location to append, and I can append right there. And I have to declare node outside of the loop. Remember, if I declare this as part of the loop, I'll get an error. I'll get an error right here because node, this initialization variable, this iteration variable, is part of the code block for the loop. Even though I don't have any braces, there's still a code block here. So node is destroyed as the loop ends, and then it's out of scope right here. Symbol can't be found, and this is just invalid code. So that's why I have to pull this initialization statement outside of the loop, because I need the node variable to live beyond the loop itself. So I have to pull that out. So this is the, I don't know, this is the cool, I hesitate to say cool way because it's a little less legible than anything else, unless you're used to seeing it like this. What I would, to clean this up a little bit and make it more legible, what I would do is this. I would make this a while loop. This will make your coworkers a lot happier with you if you rewrite it like this. Make it a while loop so it's much more clear. While we're not at the end of the list, move down the list by one node. Much cleaner to read. More developers will be able to read this code than, and then get rid of my semicolon there. More developers will be able to read this code than the code with the wacky for loop that's capped off with a semicolon. It's partly down to preference, but you really should prefer this one unless you want your coworkers to hate you. Which sometimes, I don't know, sometimes you want to piss your coworkers off, so write wacky bullshit code like that. But really, you should stick with the more legible code, more often than not. So there's my append, and then we need to get our print. So I want to do this same thing. Let's grab this code right here. So I want to start at the head of the list, and I can change this to, well, node not equal to null. I'm going to advance to the next node, but not before I print sout node.getValue. Okay. We should be all right here. Pretty sure I got all that right, but hey, if not, we'll watch it break. So let's get my print statement in just to make sure we are actually adding values. Let's add 100 values. Let's start with prepend, and I have my append prepend ds variable here. So the only thing I have to change here is changing this to my linked list prepend append. This is the advantage of using interfaces. I want to swap out my data structure, and I can do that with one change. I just did one change, and now I'm using a linked list instead of an array list. When I introduced polymorphism, I said there's never any reason to do this. You don't create an object and then immediately store it in a variable of a different type. There's no reason to do that. All it does is restrict what you can do. This is one exception to that, is when you want to make it easy to swap out your data structures or any implementations of interfaces, is if you code to the interface, you have all your variables of the interface type, it's very easy to swap out the actual implementation type that you're using that implements that interface with one change of your code, just so you don't have to trace down your code and change all your types. Everything works with the interface, change the implementation easily. That's the whole reason I set this up with an interface, partly just so I get to talk about polymorphism some more. But also it makes all of my code much simpler. This code doesn't have to change at all because it's already working with an append prepend ds variable, which has a prepend method, which has a print method. It's all defined in the interface. So I want to swap out my implementation. It's no big deal. One change, that's all I need, and everything's everything's changed. What would happen to the method if the tail points back to the head? Good question. It would go, short answer is it would go infinite. So this, I have no cycle detection here. So if the tail of the linked list pointed back to the head, the next node is never going to be null because I'm just going to do loops around this circular linked list forever. And it won't crash because I rewrote this using a loop instead of recursion. I usually use recursion. We blow up the stack overflow. This is just going to go infinite, so it's going to silently fail in that case. And my fans would start spinning up, my CPU would be pegging out, and the code would never stop running. Don't do that. Avoid your circular linked lists if you can avoid it. Unless that's your specific application, you have a circular linked list data structure, which is useful in some situations, just not for the code I'm writing. My code will not tolerate those loops. It'll just blow up. Or not blow up, it'll burn up my CPU. So we have this set up. We swapped out for a linked list. We're going to print just to verify that we are doing something. It's 100, so we should, no matter what, see like no runtime here. And we are printing values to the screen. I'm not going to count them, but I don't know. It looks like 100 values. Does that look like 100 values? I didn't realize I'm covering stuff up. I got to move my face. I'm going to move it over here. I'm going to hang out in this corner. Probably won't be anything interesting in that corner. So I'm not covering up anything with my face. Now there's something interesting. Hey, look at me. Okay. So prepending, we did actually prepend a bunch of values. We went through the linked lists and we printed them out. Cool, but let's crank this up. Let's crank this up to 100,000. And this should actually be, I'm going to predict, pretty slow. So a third of a second. Remember, 100,000 was, I think, 0.1 something seconds, 100 milliseconds plus change. So this is actually decently slow, excuse me. But prepend, I said, is a very efficient operation. This is getting back to the print statement here. Let's comment this out. I would expect to see a significant increase in efficiency, so a decrease in the total runtime. 341 gets us down to 31 milliseconds. So this print is actually going to be a lot more expensive than the print that we had with an array list because I'm printing out each value individually. With the array list, I was able to just print the array list to the screen. Let's go on a little detour with this one. I was able to print the array list to the screen. And an array list is going to use, I haven't looked at this in a while, but it should use string builder. ToString. I don't even have a ToString method. So abstract list, let's find where our ToString method is. I'm spelling ToString right? Abstract list, abstract collection, implements list. Maybe list has it. ToString may trigger initialization. Object ToString. I don't want object ToString. Oh, please, it's not it. I didn't want to go hunting down for this so much. Implements, oh, I went to an interface. I'm dumb. It's going to be an abstract collection, implements collection. It's going to be in one of these. ToString, there it is. We're creating an iterator, and we're using a string builder. So my hunch was correct. I'm sure I've seen this code before. Maybe I'm just remembering. But it should use a string builder. What this does is creates a string using string concatenation without actually creating a new string object every single time. So it's creating one string builder object, and then internal to string builder collecting all of this data together to create one single string. And then when it's printed to the screen, it creates that string one time. All the details aren't necessarily important, but it is significantly more efficient because string concatenation is actually a pretty expensive operation too. So printing to the screen and string concatenation, or I guess not concatenation, but creating individual strings. Where are we at right now? 100,000. Creating 100,000 individual string objects on the heap is very expensive, and then printing them all out individually, we have 100,000 calls to this expensive operation. That's going to be very slow. That's going to slow us down more than anything. So the prepend is very efficient. We have to create that object, but that's not really that big of a deal. And we can crank this up. That's really not that big of a deal. So once we get this print statement out, the print statement's what really slows us down. It's linear, but it has a very large constant. So now at a million values, prepending a million values, we're at 190 milliseconds, which is, just for comparison, let's get back to ArrayList, append, prepend, and append. So append is very fast with ArrayList. Prepend is very fast with linked lists. And even, we were at a million, we were at about the same. So 145 milliseconds, linked list, prepend, append, and prepend. So these are both linear in terms of n, which is a million right now. And they're about the same, 199, between 0.1 and 0.2 seconds to insert a million values if we're using the data structure's efficient insert operator. Prepend for linked list, append for array list. If we're using the efficient ones, we're doing good. But of course, append with a linked list is going to be O of n squared to insert these, because every single append is O of n, because we have to find the end of the list. We have to go through the entire linked list, dot next, dot next, dot next, dot next, to find the end, and then append. That's expensive. That's very expensive. It's going to take a hot minute for that one. While that's running, let's rewrite this code, because we can, just like we did with a queue, we can get a little more clever with our linked list implementation. With a queue, what we did was store references to the head and tail of the linked list. So let's do that same thing. Linked list node of O. Let's call it tail equals null. When we're appending, if it's the very first value, tail and head are both the same. I gotta think about prepend a little bit. So if prepend, this is fine for head, but if I can get a little cute with this one actually. If this dot head dot get next equals null, then this dot tail equals this dot head. It's probably the most compact way to do this. So if the list was empty and we prepend, we need head and tail both referring to the same node, because if we prepended the empty list, this is great for getting head to point to the head of the list. But if we just prepended to an empty list, tail is also needs to be a reference to that same node. So to check if I just prepended to an empty list, I'm going to check if next is null. If next is null, I know I just prepended the first value, and then I can update it. As opposed to checking if this dot head equals null, then update both of them, else only update the head. This is just a little more compact. It's rid of one duplicate line of code. So those are our checks. And other than that, if the list wasn't empty, prepend is the exact same thing. Tail doesn't update at all after the first prepend. Append, we got to do a bit more work here. If the head is null, actually, do we? I'll think about it once we write this code. If the head is null, then the head and tail are the same. So we have to do the same thing here. If we're appending to the end, if it's the very first thing we're inserting, we have to make sure head and tail are referring to that single node that is the linked list. Otherwise, else, this dot tail dot set next, new linked list node value null, this dot tail equals this dot tail dot get next. So we have to append the value we already have a reference to the tail node, so we're going to set its next equal to the new node with the new value, and then shift our instance variable down to that new tail of the linked list. And then all this is unnecessary. We can clean this up a little bit. Oh, can we? No, we can't really. I guess since this node is going to be the same no matter what, linked list node, I don't know if this really even cleans it up. To append, just so we don't have that duplicate code. Doesn't make a huge difference in this case. This could be to append, but I like it. It's very explicit. Tail is the same as the head in this case. If the head's not null, then the tail should also not be null if we've done everything correctly, so I can safely use the dot operator. I don't have any fear of null there, unless I have a bug somewhere else. In that case, I kind of want my program to crash so I can find my bug. And yeah, think we crushed it, chat. I think we crushed it. So now, if we go back, this is still running. Damn it! I didn't think it'd take that long. I was hoping it'd be finishing right when I was done coding that thing. So appending 1,000,000 nodes. I didn't go infinite, did I? Is it possible I just... No, because we appended 100,000 and it was fine. How come it's so much slower? Leave prepend, and this is where we went up to append. Let me paste this so I don't lose that. It doesn't override. Let's just kind of leave that sitting there. This is the only thing we added. Let's make sure we didn't mess up this append, because it shouldn't be taking this long. That's crazy. I mean, prove my point about runtime, I guess, but linked list, append, let's, I just run it here. Well, I wanted to run it side by side, but I might have a bug, because that shouldn't take that long. 10 seconds at 100,000. It wasn't, or does it? Is that just my point? Is it just making my point pretty good? Prepend with an array list. This wasn't in the 10-second range though. Yeah, this is in the half-second range. Linked list, prepend, append. Shouldn't be that slow, right? Let's take a look at this code. Did we do something dumb here? Node equals head, as long as next is not null. Advance, set next. Yeah, I mean, there's not much we can change there. Man, append is that much slower? I still don't believe that. Let me think for a little more. That's my new append. That should be fast. Yeah, this is just so slow. It shouldn't be that slow. It's got an extra method call. Maybe ArrayList is really efficient with the way maybe it groups the nodes together and moves them down in batches somehow. It should be comparable though. They're both n squared. The constants shouldn't be that different. We're under a second versus 10 seconds. Maybe it is just that bad. I don't expect that big of a difference, but I don't know. Drives home the point of linear can really get out of hand, or n squared can really get out of hand. So let's switch to our new one that we just wrote. Run the same thing, and this should be extremely fast. 25 milliseconds now for the same thing, because we're not moving through the entire linked list. That went from 10 seconds to less than a tenth of a second. 25 milliseconds versus 10 seconds. That is a significant difference. But obviously, as I just exclaimed, more of a difference than I expected, more than a difference than I think it should be. But still a huge difference, going from n squared to n. Now we can get up to, our 10 million. 10 million should be no big deal, because now our linked list, when we're a little clever about the way we're storing the references, 10 million nodes, about 2 seconds with append. Prepend should be similar, should be a little bit faster, just because the constant's a little slower. Well, just to prove me wrong, I had to go a little bit slower. But it's about the same. We're creating a new node and updating a reference. So it's about the same amount of work. I thought it would have been a little more. Yeah, I guess it is exactly the same. We're creating a node, updating a reference, updating a reference. Let's append old. Here we're creating a node and updating a reference conditionally. Yeah, this should have been faster, but maybe if I ran it a few more times and averaged it out. But point remains that very much faster. Both of these are linear runtime now. If we compare this to our array list, this embarrassed me last time, but hopefully we get a good result here. It should be comparable to our linear runtime of array list, where we're appending. This is our amortized OVN. It was about 2 seconds append, 2 seconds prepend with our new linked list implementation. Array list append should be around 2 seconds, less than a second. That's not too surprising though. That's more of a, when it was a 10 times difference, that's shocking. 2 times difference, that's the difference between the Java developers having teams of developers working for decades, optimizing the array list code, optimizing the hell out of it, as opposed to my linked list code, which I just whipped up in 5 to 10 minutes. Very big difference between those two things. But on the same order of magnitude, for 10 million, about on the order of seconds. Can you afford seconds? That's the question. When you get 10 million and linear runtime algorithm. Okay. Which is what I wanted to show with array lists and linked lists. And that's just append and prepend. There's so many more operations we can do on these. Losing random access with your linked lists versus array lists that have random access. There's a lot of difference there. Random access itself being the biggest difference. That's a huge one. But I think was there anything else I want to show here? I think that's it. Let's do, we didn't do our linked list. Let's append 100 million just to push our linked list to the limit. This should be above 10 seconds. Should be, it was 2 seconds before, so 20 seconds. We're multiplying n by 10, and it's linear, so the runtime should be multiplied roughly by 10. So it should take roughly 20 seconds, I would expect. Weird things can always happen, but I would expect it to take about 20 seconds. I was hoping that was 20 seconds of rambling. Oh, it's going to embarrass me again. Come on. Just give me the runtime. Give me the expected runtime. I might be running, let's see, 100,000. Since I need an object for every single one of these, it's going to take a lot more heap space than the array list. It's possible I'm running up against heap space limits at 100,000. How do I do this on Windows? We have IntelliJ itself, which likes to gobble up memory. But I should have a process named Java somewhere on here. I hope I don't have anything silly running, but I have Steam client running. Let's sort by memory. Well, it crashed. So I ran out of heap space, so my hunch was right at least. So I ran out of heap space, but we should be able to actually observe this. Let me run it again. And we should be able to see a process named Java jump up the charts of memory. It's possible it's rolled under here. Open JDK platform binary. Oh, example code 4 right here. Example code 4 main. So I'm at 2 gigabytes right now of storage for my 100,000 values in my linked list. So I'm running up against that memory limit. So there's going to be some 2 gig memory cap on Java. That's a setting that you can change. I can go into my settings. I'm not going to do that during lecture because I forget exactly how to do it. But there's a parameter you can give to your runtime to say, allow me to have more heap space, and it'll happily give you more heap space. But it looks like my setting, I just using the default, looks like the default is going to be 2 gigabytes of heap space before Java starts cutting you off. So it's just gets stuck at that cap until finally it says, nope, you've had enough. Let's shut her down. So let's change this to like 80 million. Maybe we can get this to finish at least. This doesn't finish in a handful of seconds. I'm just going to move on to the next thing. Or maybe we'll go to 50,000. So I do want a runtime result here. Oh, no, it did finish. So at 80,000, about 15 seconds. Not bad. I think array list at 100 million was about 7 seconds, I believe. So 80 million with our linked list is 15 seconds. So about twice as slow as Java's built-in data structure. You know what? Is it worth doing this? Let's do Java's linked list. So Java does have a built-in linked list. Linked list. Can I just call it list? New linked list in Java util. So there is a Java's built-in linked list class. Just for kind of my own curiosity, I do want to know what the difference is. So this dot list in terms of runtime, this dot list add value. Get rid of all this. Let's compare the runtimes. Printline this dot list. Let me see what add does. I'm going to check the documentation. Appends. Okay. So I'm guessing Java's built-in linked list will store references to the beginning and end. But we'll find out because we're going to run it and check the runtimes. This dot list dot add 0 value. And this is a situation where I will use the special method because I'm not sure if the actual add method is going to optimize for prepend in a linked list. So I am going to take the hint here and change it to add first, just to make sure it's optimized. Link first. Yeah, so then it just performs a prepend operation. So I don't know if add, giving it a parameter, will do the same optimization. Hell, I guess we could just test that too. But let's switch this to my Java linked list prepend append and see how we do with, let's start with append. Let's start with prepend because we just verified. I looked at it quick, but it looked like it was a legit prepend optimized. And let's run it at 80,000 again, or 80 million again. It was 15 seconds with my very hastily implemented linked list. Let's see how it compares. So far, it's looking all right. have to go down to 10 million? 15. Oh, that's like right on my implementation. Maybe you just can't do better than that. Let's crank this down a little bit because I don't feel like waiting that long for every runtime. Let's go to 10 million, run it. About 2 seconds, so that is like right on where we were. Let's see if append is optimized. We didn't look at the code. I'm not sure if append was optimized for that or not, but the fact that add is the default, that it defaults to append, kind of did indicate that it is going to be optimized and that Java's linked list will store references to the head and last, and there it is right there. Stores 2 nodes for the head and tail of the linked list. So they're doing the same thing we did in that second implementation, except of course it's Java's built-in code. There's going to be a lot of extra stuff and more complex code, more optimized code. But it looks like it's doing the exact same thing. Like those runtimes are dead on. I would expect their print method to be much faster. Where's my main? Let's crank this down to 100,000, which should be basically instant. 24 milliseconds. It's not literally instant. By the way, if you're running a game at 16 FPS or 60 FPS frames per second, you have to render the screen 60 times every second. You have 1,000 milliseconds in a second. If you divide that by 60, you get 16.7 milliseconds. That's how much time you have to render a single frame. So if you're running this operation inside your refresh loop to refresh a frame to render the next frame, this is completely unacceptable, and you just dropped a frame just to do that one operation. So it really depends on what you're doing. If you're writing a game that needs to run at 60 FPS, you have 16.7 milliseconds to do everything, which is kind of incredible that games can do what they do these days, when they have almost no time to do everything, to calculate what every single pixel on the screen should be with the high fidelity graphics and everything. It's wild stuff. Of course, this same algorithm would run on a GPU and highly parallelize it. We could get that done, but not with simple basic implementations. Anyway, so Java's linked list, 24 milliseconds. Let's print 100,000 values. Remember, my print was very horribly inefficient. I would expect this to be much more efficient. 101. Let's get rid of the Java and how long mine took to print. We have 101 milliseconds. Mine's going to take way longer. And I would suspect that if we dig into the Java linked list implementation, we're going to find a string builder and it's toString. I'm not going to dig through that again. I can pretty well predict what we're going to find. There's a string builder in there somewhere, and it's very efficient in the way that it's doing its toString. Where mine isn't. I just looped through and printed every single time. Very inefficient. Okay, so let's shift gears. We'll have a big shift in what we're doing here. We're going to throw away these data structures. If anyone who's watching live wants to see something else with this, I'd be happy to do more, but I did pretty much an exhaustive everything that I ever wanted to show, a lot more than I usually do in the fall and spring, because the last sorting example I actually don't like, so I wanted to spend more time on each example instead of doing the last one, which I thought was kind of boring, so I just don't want to do it. I don't think it's very interesting to y'all. But if we get to it, that's going to be the bubble sort. I'm gonna skip that one, unless we have time, unless I get through this quick. But I don't think I will. I think what I went through here is more helpful to see than the bubble sort. And bubble sort will be what we're going to do is merge sort. Bubble sort is going to show us a lot of the same key points that I get to make with merge sort. So let's shift into sorting. And let's just go through. There's a decent amount of code given. We've seen all this code before, except what I have on screen right now. So let's just go through this and talk about. Actually, we've seen all this too. So let's just go through what we're doing here. So we have a main method like we had before. I'm setting some value of n so we can adjust n and see the differences in runtime, how different runtimes grow with the size of n. We just did a lot of comparisons of linear or O of n versus quadratic or O of n squared. So let's do the same thing. We're going to have n and then see the difference in runtimes with these differences. I'm going to create an array list. All this is going to be with an array list. And just like we talked about before, I'm going to code to the interface. I don't really necessarily need to do it this time, but I just like giving more reminders of polymorphism. Because we're just going to work with array lists the whole time during this sorting and just sort array lists. Sorting a linked list is kind of a pain. And we need all new algorithms. We're going to sort our array lists. I have my timing code. I'm going to time how long it takes to add all my values to the list. This isn't super necessary because we just did all kinds of timings about how long it takes to add values. But I do want to still just measure that just to show in relation to the sorting, how long does just adding values to the list take. So we'll measure how long it takes to add n random doubles, still using our time trees random double method, rounding to 5 decimals, that same method. So how long does it take to add? And then we're going to time how long it takes to sort. I'm starting with our insertion sort method. We'll jump to the method in a minute. We're going to give it a double increasing comparator because we need a comparator that's going to compare doubles. This is the less than operator with doubles. I'll jump to that code in a second as well. I'm going to print all the values to the screen, then call my sorter, and then print the values to the screen of the returned list. The sort method is going to return a list with all the same doubles but sorted as the input. And print them again just to verify that we are actually sorting. We'll start with some low values of n, print them to the screen. Then once we verify that we are sorting correctly, then I'll get rid of the print statements and then crank up n so we can measure the runtime. So we want to measure how long it took to sort, not how long it takes to print the list twice. And the double increasing, since these are doubles, I do want some epsilon. Our doubles aren't going to be exactly equal. There will be rounding errors. So I will take some tolerance into account and say if it's within epsilon, if it's more than epsilon less than b, then it's strictly less than and definitely comes before b. But if they're within epsilon of each other, you know what, treat them as the same thing. It's fine. Our insertion sort, this is the same code we saw earlier in the semester. We're going to take a comparator and a type parameter, so we sort anything in any way. We're going to create an output list, iterate over every value in the input list, count how many values in the output list come before the value that we're trying to insert based on our comparator, and then insert at that location. So we saw this code before. We saw how it worked. I had examples in the slides and everything. We looked at the code and talked about it. But we didn't analyze the runtime. I said this is O of n squared, but didn't really talk about why. So we have two loops. This loop here is going to iterate over every value in the input. Our input is always size n. That's what we measure our runtime off of, is n. N is the number of values in the input. So this loop will iterate exactly n times. So everything inside this loop iterates n times. And then we have a few operations here. We have a constant time operation. A variable declaration is always O of 1. Plus this loop here, which loops over all the values in the output. Now when we're measuring O of big O runtime, we always measure the worst case. What's the worst that can possibly happen? Well, towards the end of sorting, output is going to have n minus, like the last insertion, output's going to have n minus 1 elements in it. It's going to be order n. Halfway through sorting, it's going to be n over 2. That over 2, that 1/2, is a constant, so it's still O of n. It's going to take O of n iterations to get through this loop in most cases. So this will be an O of n loop. So for O of n values, we're doing O of n work. When we have nested loops like this, we multiply the runtimes. So we're going to end up with an n squared algorithm. Inside the loop, we have O of 1 plus O of n. O of 1 plus O of n, well, the O of n dominates the O of 1, so this is just O of n. And then we have this add right here. We're adding at some unknown location. Worst case, it's going to be index 0 and effectively prepend, which we already know is O of n with all the runtime that we did earlier. So this is another O of n runtime algorithm right here, another O of n step. So we have O of 1 plus O of n plus O of n. But if we have two O of n's consecutive, we have O of n and then another O of n, well, that's still just O of n. When we add together, the terms don't increase in magnitude, we have some constant times n and some constant times n. Well, that's the same as those constants added together times n. If we factor out the constants, the n's just combine, and it's two constants, the sum of two constants times n. That's still linear. That's still a linear algorithm. So we could do a linear thing, a linear thing, another linear thing, another linear thing, another linear thing. It's still going to be linear. It's still going to be O of n. So the entire inside this loop is all O of n. So we have O of n times we're doing O of n work, so we get overall O of n squared. That's my very quick runtime analysis. In CSE250, you'll do more formal runtime analyses than this, but that's my quick hand-wavy thing. My slightly more mathematical one is that this loop, the first time it's hit, executes exactly 0 times. The second time, it's 2 times, then 3 times, all the way up to n minus 1. So we have the sum of I from 0 to n minus 1. Which is, I always forget the exacts, but I think it's like n minus 1 times n over 2, or n minus 1 times n minus 2 over 1, or over 2. It's one of those. It's something like that. But there's a formula that you can use to calculate the sum up to a value. And that formula is going to be some factor of n times some factor of n. That's going to be some n squared. It's roughly n squared over 2 minus n over 2, I want to say. Something like that. But the highest order term is going to be some constant times n squared, so it is n squared. It is an n squared algorithm. So let's see what an n squared algorithm looks like. We already saw these, so we kind of know what to expect. One quick side note, again, before we get there, I forgot one thing. I am implementing a sorter interface. I don't really take advantage of this, but I just wanted to talk about polymorphism another time, because this content always comes after polymorphism. Sorter interface says you must have a method that sorts, takes some list, and returns a list. It can be an array list, it can be a linked list, it doesn't really matter, as long as it sorts something that implements the list interface. For our purposes, it's always going to be an array list, but we can code it to the interface, and as long as we only use methods known to the list interface, it doesn't matter what we're actually sorting, as long as that data structure implements the list interface, which Java's built-in linked list and Java's array list both implement the list interface. Among others, we could use other types of lists. As long as it implements the list interface, we can sort it. Which we only use add at a specific location, which we just saw linked list does implement that. And that's it. Is that really it? That and the fact that we have iterators, meaning that we can use our for each loop to iterate over all the values. It uses an iterator under the hood. So it has to have an iterator and an add method that takes a location. That's all we use. So anything that has those capabilities, we can sort. Okay, so let's run this thing. First of all, have I been lying to you this whole time? Like, does this actually sort values? So when we print the first time, it's just a mess of data. It's unsorted, of course. And then the second time, we start with a large negative, slowly get less and less negative, less and less negative. We hit 0-ish. We don't have literal 0. They're random values. Hitting exactly 0 is highly unlikely. And then we have positive numbers that are increasing. This isn't formal testing, of course. This is the tedious form of testing where I'm like, we would want to automate that. But this is a nice, quick and dirty, gives us a reasonable amount of confidence that we're actually sorting these values. If I wanted to actually make sure I'm sorting them, I would have all my edge cases and write a formal test suite and everything. But this is a reasonable expectation that this is actually sorting. That's all we really need for this. And it took 4 milliseconds to insert. Insert should be, I did use add here, appending. So insert is going to be amortized O of n, and sorting is going to be O of n squared. And at 100, the two really don't have a difference. There's so many little factors that might have some difference. But once we crank these up, inserting is going to be much faster than the actual sorting. So let's get to 10,000. This is where our n squared algorithms in the other example started to fall apart, started to start crashing, and we have about a quarter of a second. Let's get rid of these print statements so I can actually see the first printing. So still about a quarter of a second. So we're running an n squared algorithm. That's gonna dominate the slowdown from printing the list twice. So we don't see too much of a gain from getting rid of the print statements. But 5 milliseconds on our linear runtime and about a quarter of a second on our n squared runtime. Once we hit 100,000, this is where n squared really starts slowing down on us. A quarter of a second, we already can't use that for game development on a per frame basis. It would have to be running on a separate thread than our main loop. With a website, it's maybe acceptable. Depends how optimized everything else is. But at 100,000, it's not really useful for very much of anything. If you got to wait this long for your program to do, something that you want it to do, 25 seconds is in most cases unacceptable. Depends what it actually is. If you're transcoding a video and it takes 25 seconds, it's probably okay, but not really what we want. We want something better than that. So let's crank this back down. Let's put this at 10 because I'm gonna do something different here. I'm gonna do merge sort. Oh, I did lie a little bit. We do use the sorter interface just a little here, so I don't have to change this to merge sort also. Merge sort is going to implement the sorter interface, so I only have to change one thing, just like we did before with the interface, the append prepend ds interface. I only had to change one thing. Now we're using merge sort instead of insertion sort, but we're actually not because there's no code here. It doesn't do anything. So this is the structure, the setup that we had for insertion sort. I have a constructor that stores a comparator in an instance variable, and then the sort method, which is actually being overridden. I like with my override annotations. My sort method, which right now just doesn't do anything. So the next thing I want to do is implement merge sort, talk about its runtime, and then run it and see what the runtime is. A bit spoilers, I guess, but foreshadowing. Merge sort is going to end up being an n log n algorithm. It'll be our first n log n algorithm, and we want to feel the difference. We saw linears pretty damn fast. It got us up into tens and even hundreds of millions of values without being prohibitively slow, again, depending on the application, but several seconds at the tens of million range. And a million or less, it was very efficient. N squared really starts to break down at 100,000, starts to become way too slow. At 100,000, our sorting algorithms, 25 seconds. I forget exactly what our prepend appends when we're using n squared were, but they're bad. They were slow. At least in the order of seconds. I think it was on the order of tens of seconds, but I don't remember. So let's write an n log n algorithm and see what the difference is. So let's sort this thing. So merge sort. Merge sort is going to use recursion, and it's going to use an approach called divide and conquer. You'll learn a lot about those. Merge sort is one of those topics in other classes. Merge sort is one of those topics that you're going to see a lot of times in a lot of different classes. You're certainly going to see it in 116 right now. You're going to see it in CSE150, and you're going to see it in CSE331. You'll probably see it in a few other courses. This will pop up a lot. Every time you see this, we're using this as a vehicle to be able to show you a different concept, a different thing. So it's going to be something different each time you see it. So don't fall into the trap of thinking, oh, I've seen merge sort before, I got this, and then not pay attention. Just because you've seen it in 116 doesn't mean you know what they're showing you in 250. What's up, Raja? And each time we show it, we're showing you something different. Right now, I'm just showing you a feel of n log n and showing you a more complex recursive method, and just a more complex method in general, a more complex algorithm, just to give you a taste of what that is. In 250, you're going to do a formal runtime analysis of merge sort, and then in 331, you're going to do a proof of runtime of merge sort. It's always going to be something different, something they're going to add to merge sort. So they're going to start with something you already know, and then add to it, use that to be able to show you something new. So just don't fall into that trap. I've seen a lot of students fall in that trap. I fell into that trap myself. You know, don't fall into that trap. So with merge sort, what we want to do is I'm going to write this recursively. So I know I'm going to have some recursive method. I'm going to have some this.sort call. I'm going to assume that that call works, and I'm going to build my method based on that. And I know I'm going to have some base case. My base case for sorting, the list interface has a size method. It does, right? Why is that giving me an error? If the size is 1, it's because I just didn't finish writing the line. So if the size is 1, if the size is less than or equal to 1, if the size is less than or equal to 1, I'm just going to return the input. If you give me a list that's either empty or only has 1 value in it, I'm just going to return it to you and say, bruh, this thing's sorted. This thing's sorted already. And just give it back. Like, there's nothing to do. I don't have to do anything. I'm going to use a return here, so I don't even have to have an else here. If this is true, the method ends. So if I ever make it outside of this if statement, that means that the condition was false. So I'm not going to use an else. That's a stylistic choice, I guess. I don't like my code getting indented too far, so I'm not going to do it. And now what I want to do is make a recursive call and then build my logic around that. I need to build the rest of my method. And when I'm writing a recursive method, I'm always going to just assume my recursive methods work, but that only really helps me if my recursive call gets me closer to the base case. So I have some input of size n, and I need to get closer to my base case, which is size 1 or 0. What I can do similar to what we did before, is pull one value out of the input and have what I'm left with is of size n minus 1, and then make the recursive call. I get that back sorted, and then I take that one value I pulled out and insert it into the correct location in the list, and then return that. That will work. That will sort the list. Unfortunately, what I'd end up with is exactly insertion sort. It would be doing the same exact logic, just with recursion instead of a loop, and that doesn't really help me. So there's going to be a little bit of a leap of logic. I'm not going to show you everything of why we do this. CSE116 will. But what I'm going to do instead is crack this list in half. I'm going to find the midpoint of this list, which is its size over 2. And I'm going to break that list in half at the midpoint and then recursively call sort on both halves and then build the rest of my method around that. So that's what I want to do here. So I'm going to break this thing in half. Why exactly half? Again, the math works out. The math makes it all cool to make it work for n log n. 250 will cover all that. I'm just going to say, yeah, trust me, bro. We're going to break it in half, and that's fine. So we're going to crack this thing in half, and I'm going to take the size over 2 and store that as the midpoint. This is a situation where we want integer division. I need this to be integer division because I need the result to be an int, because I'm going to use the midpoint as an index in a list. If I'm going to use midpoint as an index in a list, I need that to be an int. I can't get index 20.5. Like, I need integer division here, so I'm going to use integer division. So I'm effectively taking the floor of the size over 2, and then I'm going to take I'm using the list interface, list of t left equals input. I'm going to use the sublist method. It knows what I'm doing. It suggested it right there. Sublist, and sublist takes 2 indices, the start and end indice, inclusive of the start and exclusive of the end. So if the left list, I'm going to start at 0, that's inclusive, so I will include the first value. and then up to the midpoint exclusive, so this will not include the value at the index midpoint, but it will go right up to the value before the midpoint, from the start of the list to the value before the midpoint, and list of t right equals, and fat finger in this, input.sublist of midpoint. This is inclusive, so this list will include the endpoint up to input.size exclusive. So that's exclusive of the size. So there is no value at the index input.size. If I have an array list with 10 values in it, there's no value at index 10. The last index is the size minus 1, which is 9. But the endpoint with sublist is exclusive. So it's going up to the value before this index, which is size minus 1, which is what I want. So I'm effectively chopping the input list in two halves, the left half and the right half. Then I'm going to make my recursive calls, list of t left sorted equals this dot sort of left. So I'm going to get the left sublist sorted, and then the right sublist sorted. So I have two recursive calls. This is where we need recursion. Just like for trees, it's when we have two recursive calls where you really can't do that in a loop easily, at least, without a lot of extra work. With two recursive calls, we really want recursion. It's going to make our lives a lot easier, So we have the left half of the list sorted and the right half of the list sorted. We only have one job left to do, and that's going to be to merge these two lists into one single sorted list so we can have the original input fully sorted. So we have, Miriam's here. What's up, Miriam? So we have these two lists that we're going to assume are sorted because of our recursive assumption, and then we have to build our logic around the assumption that these just work. And with that, I'm going to write a helper method named merge. That's going to do exactly that. It's going to merge two sorted lists. And merge, importantly, is going to take advantage of the fact, or the assumption in this case, that these two lists are sorted, and then merge them together, Jack's here too, what's up? That's going to take advantage of that fact to get more efficiency. So I'm going to have a helper method. I can make it private, because nobody else needs to know about this one, unless you're writing code, which we're doing. So merge, this is going to take two lists of t. List of t, I'm just going to call them left and right here. List of t right. My favorite show's on. Are you happy you get to hear my voice late at night here? It's fun, good times. And what I'm going to do is go through both of these lists. I'm going to create a pointer that's going to point at the very first index of each list. So I'm going to start at index 0 on the left and index 0 on the right. And what I'm going to do is compare the two values that the pointers are pointing to. And whichever value comes first, I'm going to copy that into some output array list. I'm going to store it in the list interface because that's what I have to eventually return. And call this output. But it is, when I create an object, I do have to create an object of a concrete class. I can't create an object of an interface. So I'm going to create my output. I'm going to check which pointer is pointing to the value that comes first. This is the only time where the comparator is going to come into play. I'm going to call my comparator and have it compare left.get left pointer and right.get right pointer. So if my comparator says the value being pointed at by the left pointer, actually just to reduce some duplicate code, I'm going to call these left values, store these in variables so I don't have to pull them out several times, and t right value equals right.get. Left value, right value. Too loud. I'm glad I can accompany the printer. Hope we have a nice nice harmonies going on. So if the left value, what we're asking the comparator, if the left value comes strictly before the right value, then that's the one I want to copy into the output. Output.add, which is going to append, which we saw is very efficient with an array list, .append left value, else output.add right value. So this is the general logic that I want to do, is ask my comparator, does the value pointed at by the left pointer on the left array, technically anything that implements the list interface in this case, does that come strictly before the value that we're looking at on the right list? If it does, get the left one. If it doesn't, grab the right one. So ties are broken to the right value, but we're sorting, so we don't really worry about ties. They're just going to be next to each other in the list regardless, in the output list. So this is the general logic I want to do, and I want to do this until I run out of values to compare. So each time I add a value, what I want to do is increment that respective pointer. So left pointer, we're going to move to the next value in the list. If we add the right value, we're going to move to the next value in the right list. So we're going to, oops, I did value. This is where, so we're getting too, lean on the autocomplete a little too much, starts biting you. Sometimes I go too quick and it doesn't do exactly what I was going to type. So we want to advance the pointer. So whatever value we add, so we're going to look at the beginning of both lists, and whatever value we add, we're going to move that pointer down to the next value in that list as we add them. And eventually we're going to reach the end of one of these lists, and that's when we have nothing left to compare. So I want to say, well, I'm not at the end of either list. I want to keep doing this and move down, compare the values, add one of the values to the output, and then move on to the next value in that list. I want to keep doing this while I'm not at the end of the list. So while left pointer is less than left.size, and right pointer is less than right.size. So if left pointer reaches left.size, that means I'm past the end. Pointer's pointing to the value after the last value in left, so I'm off the end of the list. So if this is false, it means I hit the end of the left list. If this is false, it means I hit the end of the right list. So as long as both of these are true, then I want to keep going until I hit the end of one of these lists. Once I've hit the end of one of the lists, I need to copy all the values left in the other list over to the output. So if I've hit the end of one of the lists, I'm done with that list, and then whatever's left in the other one, I need to copy over. And I don't like overthinking this one too much. I'm going to paste my whole loop 2 times. It looks gross right now, but just bear with me. So I want to do one loop that says, if I reach the end of the right list, copy over everything that's left in the left list. So while I haven't reached the end of the left list, I don't have to compare. I don't have to do any of this stuff. I just need to add the value. I don't really need a variable anymore. That's just adding extra crap. I want to add the value that's pointed at by the left pointer and then increment the left pointer. So if I ran out of values in the right, this loop is going to clean up everything in the left. And I want to do the same thing over here. I want a loop that's going to clean up everything in the right. I don't need this variable anymore. Just to clean things up a little bit, I just need to copy all of my values over. So one of these two loops won't do anything. Because if I got out of this loop, that means I've reached the end of one of the lists and not the other. So one of these loops is going to clean up the remaining list, and the other one isn't going to do anything. And that's fine. Like, I don't know which one it's going to be, left or right. And I could add another conditional that says, if I reach the end of the left list, copy the right list, else copy the... I'll just have two lists and just be aware that one of them won't really have any effect, and that's fine. Because I don't know which one. Some runs of merge, one of them isn't going to do anything. Other runs of merge, the other one isn't going to do anything. I'm just going to put them both there. And while loops are effectively conditionals that keep looping. So I'm basically using one of these while loops as a conditional instead of having an extra if statement. And then at the end, I got to return output. And now I've merged these two lists. I have two sorted lists, and I merge them into a single sorted list with all of the values from both of the inputs, which was the last thing I needed to do with merge sort. So if I split my list in half, recursively sort both halves, and then with the assumption that those halves are sorted, merge them together, then I've successfully sorted a list of size n. Merge, I'll do a quick runtime analysis. Merge is going to be O of n. Every single time we add something to the output, which is every single iteration of a loop, we're going to end up adding something to the output. Every time we add something to the output, we're incrementing a pointer, and we never go past, like, our pointers both go from 0 to the size of that list. So we're going to end up doing linear work. If we have the sum of the sizes of these two lists is n, then this is going to do O of n work. This is going to be a linear runtime algorithm. There's a more formal proof of that. I'll leave that for 250. This is going to be linear to be able to merge these two lists. And then we're left with the question of how many times is merge called? How deep does the recursion go? I have to hand wave this proof a lot too, or else it'll take quite a while to explain it all. But the depth of the recursion is going to be log n for the same reasons that our trees are log n depth. Every time we go down a depth of the recursion, like you can think of the initial call being one call of size n, and then we have 2 calls of size n over 2, 4 calls of size n over 4, 8 calls of size n over 8. That's how we can kind of visualize the recursion. The depth of that recursion is how long it takes to go from n to 1 if we're dividing by 2 each time, which is exactly log of n. So we're going to have log of n depth to the recursion, and at each layer of the recursion, we have a total of O of n size of calls to merge if we sum up all of the merge calls for one layer. So for example, on the depth of layer of recursion at n over 8, we have 8 calls of size n over 8, which is going to have 8 calls. Each one has a call to merge of 2 lists of size n over 16, which is going to have n over 8 runtime-ish. You know, 8's a constant, so it gets a little awkward. But across all those 8 calls, it's total merging n size of 16 different lists. So it does end up being linear at each layer, and there are n log n layers. So we end up with an n log n runtime to our overall merge sort algorithm. And this algorithm is way more complex than what we started with insertion sort. Like, look at how simple this code is. Like the good old days of 115. Oh, wasn't it nice when insertion sort was so simple? We got to this, which is quite a lot more going on. There's a lot more going on with merge sort, which kind of intuitively you think, oh, that's going to be slower because it does more stuff and it's more complex. but we've actually decreased the runtime asymptotically. So even though there's more code, there's more complexity here, we actually went from n squared, O of n squared, to O of n log n. So let's see what that actually feels like. So first, let's verify that I didn't mess anything up. Let's do n equals 10, which is possible I messed something up. Oops, I need my print statements for this. Or else you just have to trust me that it sorts. Trust me, bro. Recursion's awesome and it sorts. So here's our random values, unsorted. Then we have our sorted list. It should be all of the same exact values. Our negative 91 was already in its home. Negative 5958 is right here. 58 right here. 42, negative 42. Oh, I can just highlight them. Look at that. Look how convenient that is. God, IDEs are awesome. Why would anyone not use an IDE? So it's all the same values, but they're in sorted order. They're completely in sorted order. With this algorithm, we can run it a few more times. Just make sure I didn't do anything silly that just got lucky on the first time. Looks like this is sorted. Let's crank it up to 100. Make sure it's still sorted. Not going to verify every value, but that sure looks sorted-ish to me. Let's check the ends. 9863, 9894 looks sorted to me. Not formal testing. It's not a testing lecture. I'm not going to dive into full formal testing. But trust me, bro, it looks sorted. So it seems like a magical algorithm. We're assuming that the recursive calls just happen to work. It seems really weird, especially when you're not used to recursion. But just by the magic of and joys of recursion, it works. It just works, man. It's awesome. Recursion's awesome. So let's crank this up. 1,000 should be, basically instant still. Even our n squared algorithm was fine at 1,000. Let's crank this right up to 100,000. Let's skip a few values here. 32 milliseconds to insert. That shouldn't change at all. It's an insertion in an array list. We didn't change anything there. But now 171 milliseconds to sort 100,000 values. Remember, if we switch this to insertion sort, at 100,000, we were starting to feel the pain of an n squared algorithm. Our n squared algorithm's starting to get, recursion as much as the debugger. Oh yeah, beautiful topics. Both can save you tons and tons of time, which I'm trying to kill time now, waiting for my damn insertion sort. But at 100,000, you're really feeling the pain of an n squared algorithm. If you have an n squared algorithm, you get to 100,000, whether it's appending to a linked list without storing a reference to the tail, prepending to an array list, or using insertion sort to sort your values, you're really starting to feel the pain of it. 25 seconds to sort those values. That's a long time. Again, depending on your specific application, maybe that's acceptable. Most applications that you're going to find yourself in the working world, that's going to be unacceptable. Nobody's going to wait 25 seconds for your sorting algorithm. So we write merge sort. Same, 100,000 values. I can't prove it because I'm not printing to the screen, but probably a different 100,000 values. I think I can confidently say. And it takes 0.15 seconds. Less than 2/10 of a second to sort those values with merge sort. So yes, the code got more complex, and we have to learn recursion, and there's more stuff to do. The runtime analysis is harder. We have to do divide and conquer. There's a lot more CS concepts that you have to learn to be able to get this stuff working. But boy, is it worth it when you can do that instead of double-digit seconds, your tenths of a second. That's a huge difference. In fact, we can get this thing all the way up to 1 million. Just why not? We can go up to 1 million. Merge sort's still going to be just fine. I mean, it's going to start feeling a little painful here. Again, depending on your application. I feel like I'm on repeat with that one. I should have a soundboard with, depending on your application, so I can just hit the button. A little over 3/4 of a second with our 1 million values, and just for fun, let's go to 10 million. So this algorithm, this n log n, we saw with trees how slow log n grows, and a log n algorithm is basically free. It's basically a constant runtime algorithm if you have log n. So taking your linear runtime algorithm and multiplying it by a factor of log n isn't that big of a multiplication. Our n log n algorithms are very close to our linear algorithms. At 10 million, yeah, at 7 seconds, it's going to be slower than our linear algorithms. Just for comparison, let's jump over because I forgot what the numbers were actually. Linked list, prepend, append. We're appending. This is the version with our reference to the tails, so this should be linear. 7.6 seconds for n log n. Oh, whoops. This won't actually finish in any reasonable amount of time. Printing 10 million values to the screen with my horribly slow print, I ain't waiting for that. That's gonna take a long time. A long time. Let's get rid of the print statement. And 2 seconds versus 7 seconds over on our merge sort side. So 2 seconds for a linear runtime algorithm, 7 seconds with our n log n algorithm. Obviously, time multiplying by a log n factor, that's not nothing, that's not free, but it ain't that much. 7.7 instead of 2, we got roughly a 3.5 times increase in speed. That's what that log n does for us. I'm alright with that in most cases. I think I'm alright with that. Obviously, there's a lot more complexity in all the constants. There's a lot of factors that go into that. But the point remains that n log n isn't significantly slower than linear runtime. It's not a huge factor. Not the difference between n log n and replacing that log n with another factor of n to get up to n squared. Now that's a big deal. If we're going from log n to linear, or n log n to n squared, or linear to n squared, that's a big deal. Once we have another factor of n multiplied in there, that's getting scary. If you have your nested loops, and your inner loop is running O of n times, and your outer loop is running O of n times, and you're starting to multiply these n factors and getting n squared, maybe you have a triply nested loop and each loop is running linearly. Now you have an n cubed algorithm, which is horrendously slow. That's going to be painful. Now it's 25 seconds on 100,000 versus our couple of tenths of a second, a tenth and a half of a second with merge sort. That's the difference between n log n and n squared. The difference between linear and n log n, not that much. N log n and n squared, that's a huge jump. You don't want to pay that price when you're working with any decently sized amount of data. You don't want to be up in that range with your n squared algorithms. Once you hit your 100, for me, 100,000 ish, somewhere in there is kind of not really a magic number, but that's usually where n squared is prohibitively slow. Once you get into those numbers, you got to be doing something better. You got to be doing something faster. Get your n log n algorithms out and work with those. Right? 25 seconds after a button click, like updating the gradebook in Autolab. We got to optimize that one. But updating the gradebook in Autolab. Luckily, it's only on the instructor side, so it's really low priority. But man, it takes forever. It's got to be n squared at least, and going to a database. So it's got to read from disk. Very, very slow. Reading from disk is horribly slow operation. But we have one more sorting algorithm that we want to talk about. Again, I'm going to skip bubble sort. I don't think it's as interesting as all the other stuff to talk about. But there's one more sorting algorithm that I do want to talk about, and it does use different interfaces. I kind of got to switch up the code quite a bit here. But let's where am I? We're setting up the array list. That's fine. But I want to use Java's built-in sorting method and compare those. So our merge sort, let's give it a better test. Let's get up to Whoa, those are not any of the buttons I meant to hit. Let's go up to 1,000,000. Maybe we'll go up to 10 million. Well, 10 million was 7.7 seconds. I think we can afford that. Let's go up to 10 million. Because you're not going to ever write your own sorting method. That's not something we do outside of education. Like in the classroom, where you need to learn a whole bunch of stuff. You need to learn like just how all the shit works. Once you get on the job, you're not going to bake up your own sorting algorithm unless you have a very specific application that really calls for it. That's super rare though. What you're going to do is use Java's built-in sorting method. You're going to use collections.sort, which needs to be imported. Collections.sort array. Let's get rid of the, actually let me just comment that out because I'm going to want to switch back and forth between them. I think we're done printing to the screen. Whoa. I think we're done printing to the screen, so I can just get rid of these. No, we're not done. I got to do it one more time. Okay, I'll get this. I still need the sorter. So let's comment these out. Let's do collections.sort. So collections.sort, actually I need to crank this all the way down just to verify what we're doing here, that we are actually sorting. Collections.sort will sort our values, and it will do it in place. So collections.sort, Java's built-in sorting, will actually modify your array list. So something to keep in mind, it will change your actual array list and move around the values in that array list. Where our sorting methods, we're creating a new output array list and returning that, so we didn't mess with the input at all, which can be helpful if you need to preserve that input array list. So here we are verifying that it is sorting that array list. And in fact, we can just do sort. Oh, I thought we could do that. Can we not do that? We have to give it a comparator if we do sort. Is this worth it? This isn't worth it. It does say nullable. Do I have to explicitly give it null? Oh, that's so gross. Yeah, I don't like that at all. I'm going back to collections.sort. It's my comfort zone. Collection, that needs to be plural. Collections.sort. If you're going to give it a comparator, sort will take a comparator. So here's sort, just takes a list. Here's sort that takes a list and a comparator. So you can give it a comparator optionally as another argument, but it looks like ArrayList built-in sort method forces you to give it a comparator, which can be null. Like, why not just give me the no parameter overload of it and have it call it with null internally? I don't like seeing null unless I'm doing linked lists or trees. I don't like seeing null. I think it's a little gross. But anyway, so this sorts and does a good job. Does a really good job. So this is the sorting method you should use. Whatever's built into the language that you're using, that's going to be an algorithm, just like the linked list that I mentioned earlier. Is teams of developers have optimized it for decades. You're not going to beat this method. This sorting method is going to be your optimal sorting method in just about any case if you're doing comparator sort. So if it's a sorting job that you need to do that uses a comparator, geez, if we get to where it gets to, sort, it's always layers and layers of stuff. Comparable Tim sort. If we dig down to what this actually does, what it does is runs a modified version of merge sort. It uses the same idea, but it uses one called Tim sort, which is uh, which is just a lot more optimized, a lot better than what I cooked up in half an hour or so, however long that took. Count run and make ascending binary sort. We're not gonna go. Oh, and it uses bit shift operator. Though that's a triple arrow. What is that? Cannot find declaration. Well, I knew that, but it uses fancy stuff like that. I don't even know what the triple arrow does. 2 arrows is a bit shift operator. I don't know what 3 arrows is. But anyway, it does some fancy stuff. So with all of that, what's up to Zach? What's the efficiency that we get out of that? So remember, 10 million with my merge sort that I cooked up in half an hour or so gave us about 7.7 seconds to be able to sort. So let's see what Java developers can do in decades of time and tons of optimization, lots of complexity, lots of research. They can do it in 2 seconds. That's pretty damn good. But this is where asymptotics really shine for us, is like 2 seconds versus 7.7 seconds. Yes, that is a huge difference. That was the difference between our n log n and our linear, just incidentally. That was a coincidence. I didn't expect that. It happens to be almost exactly. But it's not astronomical. It's not the difference between n log n and n squared. Like if we cook up an n squared algorithm, like that just sucks. That's a sucky algorithm. But as long as we have an n log n algorithm, it's going to be somewhat comparable to any other n log n algorithm, unless we do something really silly and really inefficient. Like it's going to be comparable. Yeah, you're going to use the 2 seconds. In practice, you should use. What am I even looking at? Main's highlighted, but we're not on. Oh, we're on the wrong main. We need sorting main. So you should use the internal sorting method that has been optimized to hell and back. That's the method that you want to use in the real world. Of course, in a classroom setting, often we ban that. We want you to learn how things actually work before you just start using the built-in stuff that does it for you. But in the real world, this is the one you want to use. That's some good efficiency there. No, that's God damn it. Okay, wait. That's why it was a coincidence that it was exactly the same timing. It's because I ran the wrong main method, and I was doing our linear algorithm from before. I was gonna say, I'm like, that's a real big coincidence that it was exact, and I did expect it to be a little slower than that. I was trying to roll with it, but I'm like, why is it 2 seconds? That's too fast. Oh, and we're still printing to the screen. That's gonna take forever. Not as long as our other one, because it's using string builder. So that would have actually finished decently fast, but I still don't feel like waiting for it. Looks like it did print the whole first one, actually. It should be slower than 2 seconds, but 4 seconds. So still same point, though. It's not the difference of an asymptotic change. So n squared versus n log n is huge. 2 n log n algorithms, yes, there's going to be different constants, and this is more what I expected. It's about twice as fast, not quite twice as fast, as the one I just cooked up, quickly and didn't optimize at all. This one that's been optimized to hell and back is almost twice as fast as my algorithm, which, yes, that's what you're going to want to use. Twice as fast is still twice as fast. That ain't no joke. But it's not the difference between 2 different gaps in asymptotics. N squared versus n log n versus linear is a smaller gap, but there's still a good gap there. Linear versus log n, or linear versus constant versus log n, again, not that big of a gap. Log n grows so ridiculously slow that if you have a log n term in your runtime, you can almost just ignore it and treat n log n as O of n and log n as constant. Roughly, there's a lot of people that get mad at me for saying that, but roughly speaking, the log n's aren't going to hurt you too much. They're very log n. We work out really hard to get log n. We learned all about trees just to get log n from linear, but we're not going to work that hard to go from log n to constant time. You actually will, incidentally, in 250. You'll do hash tables, which will get you down to O of 1 for certain application. It doesn't do everything. It doesn't maintain sorted order for sure, but it'll do a lot of important tasks, key value pairings especially, in O of 1. That's why hash maps, they're built on hash tables. Hash map lookups are all O of 1, but I'm getting a little sidetracked here. So this difference, yes, you want to use the built-in sorting method. Don't cook up your own because you're going to get that optimization. But that optimization isn't orders of magnitude differences. It's roughly twice as good, roughly twice as fast. It's good, but like, I mean, I could optimize my merge sort and cut that down a little more too. There's no reason to because I'm just going to use collections.sort in my real world applications. But I'm not going to get significant gains. It's not going to be a huge world of difference in my code. So the big takeaway and what 250 will harp on for an entire semester is get your runtimes asymptotically optimal. Don't stress the constants too much unless they're horrendous or you're at that point where you're trying to squeeze the last bit of optimization out of your program. But make sure you're hitting your right asymptotic runtimes. If you're using an array list and you're prepending in your code and you're getting to data structures up to 10,000, 100,000, you're going to feel that pain because you're hitting the wrong asymptotic runtime. The difference between appending in an array list and prepending in a linked list, there's going to be some constant factor difference. I think we saw roughly a ×2 or ×3 or something. I forget exactly what it was, but it was different. The array list was definitely faster, but not an order of magnitude faster. Like literally an order of magnitude. You probably heard that we use that out in society a lot these days. But this is literally where that comes from. Going from linear to n squared. That's what we call an order of magnitude. Literally an order of magnitude. So it's not an order of magnitude difference. That's where you're really going to see those differences in runtime. So you do need to be on the right order of magnitude. If there's a constant time solution for your problem, you got to be hitting that constant time solution. If you have a constant time solution and you pulled out the linear solution, your code's way slower than it needs to be. If you're pulling out your n squared solution when there's an n log n solution available, you need to be hitting that n log n. And again, of course, as always, let's circle back to this for one last emphasis. Unless, of course, you don't have that much data. If you ain't got that much data, screw it. Like, whatever. 21 milliseconds for an n squared algorithm at 1,000. If you only got 1,000 pieces of data, who cares? Who cares? Still, 21 milliseconds. Actually, I shouldn't even say that. At 1,000. I'll say 100. At under 100, who cares? But 21 milliseconds, we actually do care. Maybe that's a bad example because 21 milliseconds, you're dropping frames if you're doing that every iteration. You've got 1,000 game objects in your game world and you're running an n squared algorithm every single frame. You're dropping every other frame. You're going to have a meeting where you're like, gee golly, guys, I think we should go down to 30 FPS because I just can't get 60 to work. When all you need to do is get your linear runtime or even your n log n runtime algorithms. Now 11 seconds, we're below that 16.7. If this is the one expensive operation we have to do per frame, we can get away with that with our n log n. So even at 1,000, it can matter if you don't have a lot of time to work with. 16.7 milliseconds for 60 FPS ain't a lot of time. So then you do want to get your algorithms down there. So I'll say at 100. At 100, screw it. Insertion sort should be pretty free at 100. Yeah, 3 milliseconds. So at 100, then you can use your n squared algorithms. But once you hit 1,000, if you're in game dev, or 10,000 in pretty much anything else, can't use your n squared algorithms anymore. Because some people learn all this stuff and 250 and all this runtime stuff, and they'll be like, it never ever mattered in any of my programs. Well, yeah, you're building a to-do list for yourself for your 20 tasks. Yeah, who cares? You can use a n cubed algorithm. It's still going to run fine. Yeah, you might have more data because your algorithm's so slow. Yeah. That's what I got. There are a few of you watching live, so if there's anything else you want to see, I'll hang out for a second and take any requests. If you want to see some other runtime stuff. Other than that, I got this lecture recorded for the, just a reminder for, well, I don't know who this would be for. Anyone watching that's Miriam Jack, anyone who's watching who, I don't know. I don't know who this would be for, but this was a recording for the async lecture for Runtime. So I'll post this, well, once I shut down the live, I'll post the link right here. Again, if you're hearing me say that, you already found the link, so it doesn't really, there's really no point in me saying that. Just trying to kill time so you have a chance to put in requests if you want to show me something. Can you show the slowest algorithm you know? Oh. There's some really slow ones that I'm not going to be able to think of off the top of my head, but I'll whip up a slow one here. Let's go back to this main. Let's just do, so we don't talk about, in these lectures at least, I don't talk about exponential runtime. So let's just cook up an exponential runtime algorithm. I'm going to do, this is going to take a little bit, not too long, and cook this up pretty quick. I just want something that's going to sum up the values from 1 to 2 to the n. So asymptotic, not asymptotic, exponential runtime is the opposite of logarithms. Logarithms go ridiculously slow, and that's where we want our runtimes. We want our runtimes of our algorithms to be log n because that's super slow growing. We saw that our tree with 1 billion nodes is only height 30. That's ridiculously slow. Exponentiation is exactly the opposite. It's the inverse of log n. So let's do that and just see how slow the other side grows. So at 10, we would expect this to be, 1,000. Let's leave it at 10. So what I want to do is sum up the values of 1 to 2 to the n. But I'm going to have some issues here. So I can do, this is actually going to get into a few different things. So those of you who do want to see this stuff, it's going to be cool. Math.pow, we can do 2.0 to the n. And let's pre-compute that. We will have to think a little bit about some optimizations. It might not matter, it might matter, but I don't want to have to compute this every iteration of the loop. So let's pre-compute this. Let's do int 2 to the n. It's a weird variable name, but I'm rolling with it. Oh, actually, we do get away with this. Okay. 2 to the n. Pow returns a double. So I actually do get away with this. Less than a double. I was going to talk about overflowing an int. I still might have to. But let's just use doubles for now, and we might get away with that. So sum, I just need to do some thing inside this loop. I need some operation in here so it does something. Or else the compiler might optimize it away and say your loop doesn't do anything. I'm getting rid of it. So we have to do something in here. So sum plus equals I. I will actually overflow this int at some point. Not yet, because n is 10, so 2 to the n is going to be about 1,000. It'll be 1024. And then s out sum, see what we get, and then just so my print statement is fine, I'm just going to say it took this long, this many milliseconds. So let's run this, see how long it takes, and it took 0 milliseconds and gave us this value. Actually, I'm not even that concerned about overflowing in an int. I am because the loop will go infinite. So we'll talk about that as we go. So let's set n to 20. So 2 to the n. Let's print out I I can use symbols here because it's not a variable name. 2 to the n. 2 to the n. Let's print out what 2 to the n is, and then run it. 2 to the n is about 1,000,000 at this point. And our sum is a ridiculously large value, 5.5 times 10 to the 11. At 30, we should be hitting 1,000,000,000-ish. We shouldn't overflow an int yet. An int, we are using powers of 2, so we know we can get to 30 because an int is 2 to the 31 minus 1. So once we hit 31, we should be going infinite. But even at 30, we already got some good runtime. So this is about 1,000,000. So if you have 30 values and you have an 2 to the n runtime algorithm, at 30 values, it's already taking over a second. This is an unusable algorithm, even with very low values of n. And once we get to 31, we should be going infinite at this point. Just because we're using ints, it's not going to finish. It's going to think for a while and never finish. So there's a quick fix to that. We change this to a long. And the reason this is so slow is every time we increment n by 1, we're doubling the runtime. So if we increment this to 32, 312, ooh baby, 2.7, but 2.5 seconds, we're going to go up to 5 seconds-ish for this change. So it's the opposite of when we take a list of size n with merge sort and we're cutting it in half each time. How many times do we have to cut something in half to get to 1? Well, that's log n. If we're going the other way, if we're doubling each time, that's our 2 to the n because we're doubling, then doubling, then doubling. This is a ridiculously fast-growing algorithm. It's this is, if you have, there's a bunch of math puzzles with this. One of them is the king one. I got to remember off the top of my head. I'll probably mess up some of the details, but like a jester goes to the king, I think it is the context of it. But goes to the king and says, hey, makes a deal with them. They're talking about how much to pay for his services or some shit like that. And takes out a chessboard. Jester takes out a chessboard and says, okay, on the first day, you can pay me, on this square, just pay me 1 penny. And then on the second day, on the next square, you'll pay me 2 pennies. On the next square, you'll pay me 4 pennies. On the next square, you'll pay me 8 pennies. I feel like I might have messed it up. I forgot what I was saying. Then 16 pennies, but it doubles each time. And it'll go, as soon as we get to the end of the chessboard, which is an 8x8, 64 squares, once we get to the end of the chessboard, then you have paid me in full. And the king says, yeah, sure, that sounds, I mean, in the first week, I'm paying you less than $1. That's fine. But once n gets to 64, I should have had this running while it was going. N at 64, 2 to the n is this ridiculous number. So just on the last day alone, this is how much money that jester's getting paid, which is more money than in the entire world. Every country, every currency, everything. That jester owns absolutely everything many, many, many times over. 2 to the 64 is a stupidly large number. It's a ridiculous large number. It's 1.8 times 10 to the 19. So 1.8, but move this decimal place 19 digits over. Very, very, very large number. Slightly larger, about 2 times that maximum value of a long that we saw earlier. And this loop ain't never gonna end. It's never gonna. Shouldn't say never, but it's really never gonna end. Slow growth, fast algorithm. Hell yeah. Why do you think there isn't that much money in the world? It all went to the jester. Yeah, really. Which, by the way, you all know this now, but can be a little deceiving. The difference between 2 to the n and n to the 2 n squared, which we talked about a lot today, that gets us up to like 100,000 before it's really getting slow. 2 to the n, I mean, all I did was switch the values. Like, what's the big deal? And n's the bigger value. Raising, multiplying n twice, that sounds more than multiplying 2 any number of times. Like, that's crazy. But no, this grows stupidly fast. 2 to the n, like this isn't gonna end. Like I could let my computer run for quite a while, probably till the end of time, before it finishes with n equals 64. Do a little bit of math, I guess. I don't remember the runtimes. What was it, at 30? I think it was a few seconds. Let's say it was 1 second. It was a little slower than 1 second, but let's give it the benefit of the doubt. Say at 2 to the 30, it was 1 second. So 2 raised to the 64 divided by, can I do quantities? 2 to the 30? Is that going to work on this calculator? Yeah, it did. Which is 2 to the 34. It's the same as 2 to the 34. You just subtract the exponents. So 2 to the 34, this many seconds. It definitely did that right. Order operations would do the exponentiation first. So this is 2 to the 34. This is how many times longer n to the 2 to the 64 will take than 2 to the 30. So we're going to wait this many times more. So if we're saying 2 to the 30 was 1 second, let's see how many, that's how many seconds. It'll be this many minutes, seconds, minutes, hours. It'll be this many hours. I want this calculator to be bigger. Can I rant about resizing shit? Like, why is it 1 pixel that I got the magic pixel there. It's 1 pixel that I have to be able to resize a window. It'll be this many days. It'll be this many years. It's not finishing. 44 years before this is going to finish. I'm not waiting that long. Sorry, guys. I mean, it's just not waiting that long. That's a long-ass time. If we take this, let's just say 120, and do the same math. So 120 minus our 30, this is 2 to the 90 seconds. 2 raised to the 90 seconds divided by minutes, hours, days, years. It's this many years. 1,000, million, billion, trillion, quadrillion, 39 quintillion years. The universe will be exhausted. The heat death of the universe will occur before we can finish computing 2 to the 120. For the asymptotic runtime algorithm, if n is 120, the universe will end before your algorithm. This is a useless algorithm. If your algorithm is 2 to the n, it is a useless algorithm except for values like less than 20. Maybe they're fine. But if you're using an exponential algorithm in your code, you're wrong. You're hopelessly wrong. There is still a benefit. That's how old Paul is. There is a benefit to this, though. The nice part about 2 to the n algorithms, these exponential algorithms, is on the side of cryptography and security. If you can prove that it takes 2 to the n to crack your crypto system, now we're talking. because now you can build cryptography that is basically uncrackable, or at least there's no known methods. You know, cryptography is a whole separate thing. It's a whole different lecture, a whole different class. But that's where exponentiation, this exponential runtime, actually does help us a lot. It is the basis of all of cryptography, all of encryption on the internet. It's all based on the fact that that there are very slow runtime algorithms out there, and they run so slow that we just can't break them and before the sun burns out. So we're pretty safe using them out there. We're pretty comfortable using them. The downside of cryptography is that we don't actually know that our algorithms are hard to break. We just kind of feel like they are. But like I said, that's a whole separate thing. Very fun stuff. If you're interested in cryptography, there's a lot of cool stuff for that. Your computer could probably do it in a few minutes. You can afford one of them GPUs, can't you? Yeah, you can just crank this one out right then. You should go break encryption. All right, I'm done. I gotta go to bed. If you're watching this async, it is 12:38 a.m. I'm done. I'm gonna stop this. I ain't gonna wait. What was it? 344 years. I'm not gonna wait that long for this thing to end. Sorry, guys. Do you think if you can verify a solution in polynomial time, can you solve it in polynomial time? Whoo, baby. I'm on the side of no, though. I think p is not equal to np. It's so many people have tried to find it. I don't know. I feel like if there was a way to do it, that we would have found it by now. But at the same time, we haven't found a proof. And you can say that use the same exact logic for if there was a proof that it wasn't, then we would have found that too. So yeah, it's going to remain one of the big mysteries for a while. I'm on the side of no. It's kind of the safe bet. Everybody thinks that it's not, but it's probably not. They're probably not. Probably can't be done. All right, on that, I'm out of here. See ya.